Okay. Yeah, so our topic today is we're going to be talking about a next generation cement evaluation tool. I'll introduce myself first of all. My name's Joseph Guyan. I'm the digital product manager for ANSA Data Analytics, and we're specialized in cased hole data analytics. So I've been working with this data type for about 20 years now, and I've spent the last 13 of those with ANSA. We've got a team of about 10, 11, 12 people, all working on the same data. Over the years, I've worn a few hats. I've been manager of the analysis team. I've done the reports myself. But lately, I've been really enjoying these webinars, so I hope you get a lot from that, and thanks for spending your time here. For those of you who are just joining, there is a poll, hopefully live. Hopefully you can see that. So make sure it's just a few questions. If you can answer those, that'd be great. So today is going to be a great chance for you to learn something new, get familiar with the kind of analysis that we do, and at the end of the day, you can ask us some questions. So just on a quick housekeeping note, we are recording the session, and that's why we'd like to keep the questions and answers until the end, so we can stop the recording at the right time, so you can keep yourself private at the end there. But if you do have any questions as we go, feel free to put them into the chat and we'll get to them at the end. And if we do run out of time for answering questions, then we'll catch up with you after the webinar. First, I'd like to ask a little bit of forgiveness because this is going to be quite a broad topic. We're going to be introducing 2 or 3 big broad topics. So hopefully we're not going to go over anybody's heads, or hopefully we're not going to go too shallow as well. But maybe if you see it as a bit of a teaser for the main event, and like I say, please feel free to catch up with this after the webinar. So I'll spend maybe just 5 minutes introducing the topic before I hand over to Faris. So the agenda roughly will be, well, not roughly, it will exactly be this: the role of cement. So what is it doing in your wells? What role does it play? And perhaps short examples of cement failures and the consequences of those. How do we evaluate the cement in your well? So an overview of sonic logging methods and what they can show you. What makes it difficult? So the limitations of logging tools and real-world obstacles. We'll touch a little bit before we get into it in detail. We'll touch a little bit on ultrasonic tools and what they add. And then that leads us into the main event, really, where we spend most of our time. We're looking at an example that we've seen recently of a newer tool, a Nusonix from Cereus Ultrasonic Limited. So we'll be looking at that tool, and Faris will be talking you through more from an interpretation standpoint. At the beginning, in your wells, where is the cement and where does it go? What role does it play? So again, the construction of these wells is a very broad topic, and this is just a very quick overview with a couple of nice pictures just to make it clear for you. But if you can imagine the cement being placed in the annular spaces between your well casing and the borehole wall, and in some cases between other casing strings as well. Its purpose is to seal and support the well. It must ensure critical aspects of isolation, and ideally it will continue to function in this way for decades after completion. So what happens when the cement doesn't bond properly, or perhaps degrades over time? Some of the consequences can be severe. For example, fluids migrate between production zones, or perhaps all the way to the surface, and perhaps into water aquifers as well. Cement failure can take place in different parts of the construction, affecting production, safe operation of the well, and preservation of the environment. So that's why evaluating cement bond integrity isn't optional. It's managing your well integrity can be seen as your license to continue operating. And that's what brings us on to the technologies that we're going to discuss. Once it's placed in the well, you can't look at it, you can't inspect it directly. So we're relying on acoustic logging, essentially, to evaluate how well it's bonded to the casing and formation. And I'm sure you're all familiar with the cement bond log, or CBL. So again, another big topic for you, logging in general, big topic, the tool technology that exists already. So very quickly, this technology works by measuring how the acoustic waves travel through the casing, and specifically the amplitude of the signal traveling down the casing, which can give you information about the cement to casing bond. So that's your first bond there. between the metal and the cement. Another aspect of that measurement is the VDL, or variable density log. That's the rightmost track of that example there. Now that gives you information about the cement to formation bond. So that's that other side of the picture there, in the simple case where you've got one barrier, one metal barrier. So using the VDL and the amplitude log together gives you the ability to interpret the cement job and evaluate the cement job. Now, what makes it? Why isn't it as easy as it sounds? So it's partly because the cement placement itself is going to be imperfect. The casing itself can be off-center. The cement takes the path of least resistance when it's poured, and perhaps channels along one side. Over time, you might develop what we call microannuli, so very small gaps in between the metal and the cement, allowing fluid migration. When we think about CBL, VDL measurements, typically this measures an average acoustic signal around the casing. So that means that if you've got an 80% bond, 20% channel, the tool may still report a good bond. Now, that's oversimplified, but because there's some nuance there, of course, with other tools, segmented tools and radial bond tools, which do give you detailed variations around the circumference. So using the CBL VDL alone could result in an incomplete picture, depending on what your logging objectives are. So we're going to add something else to our toolbox, which is ultrasonic inspection methods. So these tools emit high-frequency pulses and measure the reflected signal at the casing-cement interface. What's different here is the ability to scan the full circumference of the casing using a rotating sensor of some sort. The result is a radial map. Now, Faris will be talking about this in great detail shortly. Ultrasonic doesn't necessarily replace CBL or VDL. Sonic tools are still widely used, of course. But when localized defects matter, whether for regulations or environmental or operational purposes, you could look to ultrasonic for complementary detail. So choosing between them depends on the objective, well conditions, and required resolution. In many cases, the best insight comes from integrating both approaches. And that's actually present in the example we're going to talk about today, which is a nice spot for me to hand over to Faris. So take it away. Thank you very much.
Yeah, thank you, Joe. Thanks very much. I believe I didn't introduce myself. So let's start with that, actually. So I'm currently...
Apologies.
Yeah, that's fine. I'm currently wearing a hat of a senior analyst with ANSA Data Analytics. I've been working for almost a decade on well log analysis, and especially on cement and pipe inspection logs. Yeah, that's done. Let's now introduce actually the Nusonix tool, shall we? Yeah, it's an ultra high bandwidth ultrasonic tool manufactured by the company named Cereus Ultrasonics Limited. It basically works in virtual. Oh, the slide's gone.
Oops, sorry.
Oh, yeah. So yeah, I was saying it works virtually in any liquid or pressured gas. The coverage or the operating range of this tool is pipe sizes ranging from 278 to 13.38 inches. As other tools in the industry, it can provide both pipe inspection and cement measurements, so nothing new. As it concerns the principle of measurement, quite simple. Transducer starts pulsing or transmitting an ultrasonic wave towards the target, which is the inner wall of the pipe here. Part of it of this wave will reflect to the transducer, as we can see here in the middle part of the image, and a small bit of it will transmit to the steel or whatever material the pipe is made of. And within that wall, it will bounce back a few times, losing energy each time it collides with the back and front wall. So all of these reflections will be recorded, as we can see here in the right-hand side image. So this reflection will be recorded and transferred into frequency domain in order to compute the thickness of the wall. And in the next slide, we can see it in a bit more detail. So how the signal looks like. If you can give me the next slide, Joe, please.
There you go.
Yep. In the first part of the image, we can see the full waveform where individual reflections are clearly identified thanks to the high bandwidth. Right below it in the number 2 figure, actually is one of the most important for us today in this webinar. We can see the envelope of the decay rate of these reflections happening at the interface casing cement, which enables us to calculate an acoustic impedance. And the last part of this image is the signal frequency, the signal in frequency domain. As you can see, all the harmonics are picked up by the tool, and the separation between each one of these harmonics is used to determine the thickness, as previously mentioned. The next slide shows actually a comparison between conventional tools and the Nusonix. Here it is. As you can see in this image, like I said, it shows a comparison between the Nusonix on the right-hand side of the image and other ultrasonic tools in the market. We call them conventional tools for the purpose of this webinar, and they're on the left-hand side of this image. As you can see in the upper half in time domain, the first reflections bandwidth is narrower in the Nusonix waveform, but at the same time, when looking at the frequency domain, we do have a broader and richer band to work with. Same goes for the echoes in the second part of the image. There are recorded right after the first reflection, and you can notice how well defined the back reflections are in the Cereus tool compared to conventional tools. If you can give me the next one, Joe, please, so we can see what concretely the Nusonix give us. And it actually gives us a couple of options to play with for the cement interpretation. We do have on the right-hand side the NTE map, which is the normalized tail energy. And it is, I would say, the conventional method to do things. It's largely used by most of the tools out there in the market. It is defined as the measure of the normalized tail energy of the casing that's influenced by the casing rear face interface. This measurement is then normalized to the front face casing. So you have kind of a ratio. In the opposite side, on the left-hand side, the Decker map, which is the other option that Nusonix tool gives us, which allows us or allows the tool to kind of stand out from the competition. What it is defined as the rate of attenuation that's observed in the back wall reflection of the casing. It is simply calculated by taking the ratio of the decay between the back wall reflections, and it serves as an indicator to compute or calculate acoustic impedance at the boundary behind the tubular, right at the boundary. And we'll talk about that in a bit. Next one, please. All right. Well, yeah, let's move a little bit from the theory for now, and let's dive in an example so we can see together what's the added value of this tool in terms of cement evaluation. Before actually looking at data, here's a bit of context for this well. This customer wanted to log the Nusonix tool in an injector well, completed with a 5.5 inch liner, and there's a 7-inch casing behind it. So small part of the log towards the top, we will be in a dual string section, and it will be interesting to see how the tool behaves in such conditions. There's also 100 meter of perforation. So this tubular has been perforated between 2004 15 meters and 2003 15 meters in order to squeeze cement and isolate the target so the targeted formation here. So they're going to do the perf, wash, and cement. And as per the standard of the PwC, at least 15% of the formation needs to be isolated to call it as a successful operation. It is worth noting that an RVT as well has been logged along the Nusonix, and it is really handy since we'll be able to compare how this new jam tool compare against sonic radial bond logs. Oh, by the way, the formation here is called the Z1 formation and is mainly composed of anhydrides. So yeah, keep that in mind. And now I'm gonna leave PowerPoint and go directly to the software. So we can see, we better see together the data set. So let's zoom out. So we do have the entire, let me know if you can see my screen. Just make sure everyone can see it.
Can't. We can't.
No. Not yet, no.
Not yet. Okay, let me just restart sharing. Share it. I think you can now.
Yeah. Thumbs up.
Yep, cool. Yeah, as you can see, lots of tracks and lots of things going on here in this data set, but we're going to break it down into features of interest, and I am going to walk you through each of the relevant tracks. Some of them most of you are probably familiar with, while for the other ones that sounds new to you, we'll sort that out in a bit when I start going through them. First things first, I've mentioned previously two important things here. We do have 100 meters of perforation, and it can be seen from the radius map. Here, the red dots, you can see it from the radius map. So the first track I introduced today, the radius map. We can also see those perforations here in the echo map, which is basically the energy level measured by the Nusonix tool. And we can see the perforation in a brighter color here. They are slot shaped features. The second important thing is the formation's nature. Remember, I said that the Z1 formation is composed of anhydride, which are well known for being fast formations. And there clearly are here. And how can I tell it? Well, looking at the VDL, so here on the right-hand most track, we do have a VDL. I plotted along the VDL the 5 foot travel time, and here in blue, and a gamma ray in white. As you can see, in front of the cemented zone, well, before that, above that part, we do have a constant travel time and relatively marked pipe arrivals. So we do have straight line here, but after entering the perforated interval, or AKA the well cemented zone, we do see some variation, some wriggles here early on the VDL and as well in the travel time, the 5 foot travel time, which is characteristic of the fast formation. It basically starts at the top of the perf, which does make sense because that's where the cement has been squeezed. So they started squeezing from the bottom perf up to this point, the top perf. So yeah, it does make sense. It's worth noting that the Nusonix isn't really impacted by the fast formation. Why is that? Well, because obviously the biggest part of the signal, of the returning signal, isn't going to make it to the formation, which is not the case for sonic logs, where the signal reaches generally formation if there is a coupling or material, cement in this case, in between. This can lead to elevated amplitudes and higher interpretation uncertainty, because you won't be able to accurately tell if the cement Yeah, so I've been talking a lot, but I didn't really explain why this tool is different. So yeah, I think let's do it. Let's do it now. Let's go. It is fairly explanation, to be honest. So first thing, I need to make this track a little bit larger and zoom out so we can see the entire range. Let's make it a bit more large here. We can see two curves. We do have a black one and a red one. The black one is the average Decker. I introduced a quick reminder for both of these curves. Decker is the Decker rate of the reflection observed in the back wall, while the NT here in red is the normalized tail energy of the rear face to the front face interface. In a nutshell, the black curve looks a few micrometers behind the back wall of the pipe, while the red curve, the average NT curve, it looks slightly further than that. And this means we can picture the presence of potential microanalysis by comparing how the impedance changes horizontally and how we do it practically here in the log. What I like to do is overlapping the average Decker and average NT in a steady, well-cemented zone, which we're fortunate here to have. This well-cemented zone is well-defined across the perforated interval. So we can see that these two curves overlap perfectly. And what we want to look at, want to spot any kind of separation, significant separation, and flag that that zone as potential microanalysis. Little bit of, I would say, a further explanation here, or I would say a little bit of attention need to be put here, because this applies uniquely in when we are above the cement cutoff, which means which is materialized here by would say the absence of shading, because the blue shading here indicates that we're below the cement cutoff for both average and average Decker and average NT. Both curves have their own cutoffs, cement cutoffs. So we need to be above that cutoff and have that separation. So if you look, I'm gonna actually break down this interval into three separate zones, so we can talk about that in more detail. So the upper part here, which basically starts slightly above the perforated interval, we do have a significant separation, but it's not related to microanalysis. As I said, both curves are indicating a liquid bearing zone because the readings are below the cement cutoff, as you can see the blue shading here. The mid part of the log, which we've covered a bit, is this well-cemented zone across the perforated interval. We do have a strong indication of good casing to cement bond. It does make sense since the formation arrivals are quite strong here, which is generally an indication of a good bonding. This overlap continues. Let me zoom a little bit up to this point, 2004. 37, let's say 2004, 37. Below this point, we're entering again a liquid filled section. Yeah, note here, if I zoom out in again, note here that the RBT, so the sector map, and also well the amplitude, the sector amplitude, shows that this liquid zone is a bit shallower than the one indicated by the Nusonix tool. This is likely because of a thinner cement sheet below the bottom of the perforated interval, which is here. So that kind of explains the discrepancy in the readings. And towards the bottom, the last part of this log, we do have sunscreen installed here. So we do have 1 and 2 and 3. And a fourth one, you can see it also in the sector map. We do have 4 sunscreens installed. What these sunscreens do to this log is basically attenuating the amplitudes of the RBT. However, we don't see any impact on the Nusonix map. You can look at the Decker map. We don't have any change in behavior or trend or any significant attenuation in the map. So it's kind of it kind of acts like a safeguard when it comes to interpreting the cement behind completion items or across different pipe weight, because it can be challenging sometimes. Sometimes you will have a contrast in reading over the impedance. So yeah, it can be challenging. So that's a positive point. And this leads me to the last bit of this walkthrough, which is related to the integration of pipe inspection channels. Like I like to say, if you don't use it, you will lose it, definitely. These channels are provided by the Nusonix tool and other conventional ultrasonic tools, actually. They help you better understand some weird-looking features or hard to explain ones, weird curve behaviors as well. For instance, I do have a couple of examples here. When looking at the cement maps, the video as well, we do have some significant attenuations here. When you first look at it, it kind of matches the gamma as well. So we might say that we do have some shale bonds here and here as well. But when you look closely, and when looking at the radius map and at the echo map as well, right below the shoe, we do have some buckling patterns, potentially buckling patterns that are some other features as well are introduced by this buckling, because the centralizers of the tool will first enter that buckling, and then it kind of decentrate the tool, and it goes some, I would say, echoes of the main feature. But the main thing I want to talk about is this feature can cause misleading interpretations. I've seen many times deformations, degrading the cement bonding within a localized zone, and you need to explain that. And if you don't look at the available other channels that look at the inspection mode channels, you might miss that. So it's very important to include everything available to you. Let's look at another example here towards the bottom. This one is more subtle, but the echo map picked up this inner groove wall. We can see that this inner groove wall kind of is mirrored in the NT map, not in the Decker map, because we do have a different sensitivity here. So yeah, make sure to check all the maps available to you. It's even valid for the acquisition when doing, for the field engineer, when logging ultrasonic tools. It will be a very good habit, a very good thing to do is to plot amplitude map, radius map, travel time map, thickness map, when you do log a cement evaluation log. Along the impedance, you want to have a look at those maps in real time, if it's possible, and because it will help you, would say, build more confidence on your impedance values. Long story short, use whatever curve available, whatever cement info, whatever well info you might have, because it could be the missing part you need to get your interpretation to the next level. It is even more the case when you do have tools like this that offers you different options to play with during your analysis. Yeah, I think that will conclude today's walkthrough.